All right, so let's go through an example of a confidence interval here. And what I have written out is the same things I said for the example on the slide, which is that let's say we have 100 people who were assigned sentences for robbery in New Jersey, and in that sample of 100 people, we had a mean sentence of 10.6 years. So our n, or our sample size, is 100 people, and our sample mean, or x bar, is 10.6 years. So if we were trying to make a good guess as to the average sentence length for robbery in New Jersey, our best guess would be that it's 10.6 years. Because this is the value that we have in our sample. We know that our sample is going to look like the population on average. The problem, though, is, as I said before, it's always possible that our sample is going to be different from the population on some characteristics just by chance. And so our goal in creating a confidence interval is to create a buffer around the true population mean that, is likely to include the true population mean at some level of certainty. And I like to draw it like this, just as a representation, where we have our x bar at 10.6 years, and we want to find this interval where the true population mean is somewhere in here. And the question is, what are these values on either side? So, what is the actual interval that is likely to include the true population mean based on some level of confidence? And we're going to need a few things to calculate a confidence interval. The first thing is going to be some sample statistic, like x bar, which is the mean. You'll need population standard deviation, or an estimate of it. And you'll need your level of confidence. And we talked about what your level of confidence is on the last couple of slides. So your level of confidence is just how much certainty you have that this interval around your sample estimate actually includes the true population mean. And for this example, we're going to be looking at a 90% confidence interval. And as I said before, the level of confidence is totally up to you, the cruncher of numbers, or in this class it will be up to me, the person who makes you crunch numbers. So for this example, we're looking at a 90% confidence interval. So we want to be 90% certain that the true population mean is in here somewhere. And here's where we're going to pull in some ideas from last week. So what we learned last week is that in a sampling distribution, you have all the possible sample means that you could get. So let's say this is 10.6 here. And some sample means are going to be more likely and some sample means are going to be less likely. So for now we'll say this is the true population mean. So this is what we learned about last week. This is your typical sampling distribution for means, where you have means that are likely, and then as you get further away, you have means that are less likely. And we know that when a sample size is greater than 30, this sampling distribution is always going to be normally distributed. What we can do then is just draw this sampling distribution on top of our best estimate here and use it to figure out how likely it is that we're going to get sample means that are close to this estimate or far away from this estimate. And so what we're doing here is saying that even though we don't actually know the true population mean, we're going to, sorry, I'm on a different table than usual. We don't know the true population mean, but we're going to use our point estimate here, so 10.6, our sample mean, as our best guess, and go from there. So we're going to redraw our sampling distribution right on top of this buffer that I have here, where 10.6 is our best estimate, which was x bar, and we're going to figure out what values include 90% of the possible sample means that we would have on either side of this. Because what this tells us is that based on what we know about how these sample means are likely to be distributed, with this as our very best guess for what the true population mean is, we can be sure that 90%, you have a 90% chance, of getting a sample mean between two values. So if this is your best guess, again, our sampling distribution could tell you we have a 90% chance of getting a sample mean that's between two values. So we're essentially doing the opposite of what we did last week, which was looking at two values and figuring out what the probability was of getting some outcome that was between those two values. And so in other words, we're going to look for the interval around our point estimate that includes 90% of the area under the curve here, because there's going to be a 90% chance of getting some outcome within that interval around the true population mean. So how do we go about doing this? So I'm going to briefly redraw that picture that I had on the last slide. It shows that 10.6 is our best estimate for what the population mean is. And again, we want to find the interval around that where you have a 90% chance of getting a sample mean within that interval. And we want to know what these values are. Well, anytime you have a normal distribution, you can convert it to z-scores and convert it into a standard normal distribution. And then once you do, there's all sorts of things you can do because we have a lot of properties about it that are already known. So this is mean sentence length, x bar. And again, we're looking for the interval on either side of 10.6 here, where we have a 90% chance of getting a sample mean that's within that interval. Because that'll tell us the buffer around our point estimate, where you have a 90% chance that you're going to have the true population mean in that interval. And I want to just be very precise about the language here. Technically, either the population mean is in the interval or it isn't. So it's not correct to say that you have a 90% chance that the population mean will be in the interval. Instead, you have to say there's a 90% chance that your interval includes the population mean. And what this means, in other words, is that if you were to do 100 samples like this, 90 times out of that 100, the interval that you come up with would include that population mean. So that's another way to think of that level of confidence. But I'm going to go back to the nuts and bolts of how we do this now. So we're going to convert everything to a standard normal distribution. And again, we're going to keep everything else the same. When we make a standard normal distribution, The only thing that we're changing are the units on the x-axis. So instead of having our mean sentence lengths, now we have z-scores. So we want to know what this z-value is and what this z-value is. To have 90% of the area under the curve surrounding our mean value here. And similarly to the 68, 95, 99, 7 rule, there are specific z-scores that correspond to different confidence levels. So before we were saying, 68% of the area is within one z-score or one standard deviation of the mean. And now we're going to be looking at it the other way, and we're going to be looking at the z-scores that correspond to different confidence levels. And for this particular example, based on what we know about the shape of a standard normal distribution and how much area falls in different places, we know that 90% of the area always falls within plus or minus 1.645 z-scores. And this number might look a little bit familiar, and if you think back to the table that I showed you on the last slide before I came over to the document camera, this was one of the numbers on that table. And so there are, as I said, particular z-values that correspond to different areas around the mean. And these are known as critical z-values. So the critical z-values that I put up on the slide are the ones that it's helpful to know. So they're for 90%, 95%, and 99% confidence. It's also possible to figure out what these values are using the z-table, but this semester I'm not going to make you do that. If anybody wants to figure it out themselves and tell me how they did it, I'll consider that an extra credit opportunity. But for now, just take my word for it that we know the values that encompass 90%, we know the values that encompass 95%, and we know the values that encompass 99%. And you can find those values again on that table of critical z-scores that's on the slide. And so again, we're using our basic property of the normal distribution, which is that you can convert everything to z-scores, and then you know based on the z-table what different values correspond to what areas. We're going to use that to say that we know that 90% of the area under the curve is always going to fall between plus or minus 1.645 z-scores on either side. So for our 90% confidence interval, we're trying to figure out which values on either side of our best guess here, our point estimate, correspond to a 90% probability of getting a value in this range. To do that, we're going to use these z-scores that we found, so our critical z-values, to figure out what our question mark values are here. And to do that, we're going to use something called the confidence interval formula. And specifically, your confidence interval formula is going to look like this. Your confidence interval is going to be equal to your sample mean plus or minus your critical z-value times your population standard deviation divided by the square root of the sample size. And this should look familiar here because this is also the formula for standard error. So you could write this out as well with just standard error in place of this, but I think it's a little bit easier just to leave it in terms of these values here. So again, I'll just write this out. X bar is your sample mean. Z is your critical z-value. And N is your sample size. And then finally, sigma is your population standard deviation. So now whether or not you followed my explanation as to how we got here, what we're looking at is just a formula where you can plug things in and get a confidence interval. And so I'm going to take the values that we have for this example and start plugging them in. Oh, sorry, no, I'm not. And let me back up there. The reason for that is that we still haven't addressed this population standard deviation. Sorry, I'm following old notes that are slightly different than what I meant to do just now. Okay, so we have this formula, but we're missing one thing. And the thing that we're missing is our population standard deviation. And the population standard deviation is something that it's often really, really hard to know beforehand. Why is this? Well, you're using your sample to try to estimate the population mean. How likely is it that you already know the population standard deviation? Usually, if you don't know one population parameter, you don't know a different population parameter. So because of that, we're going to learn to estimate the population standard deviation instead of knowing it for sure. So I'm actually going to leave you with this formula here and not plug anything in, and then go back and briefly talk about estimating this population standard deviation. And apologies for these slightly disjointed notes here, but hopefully the point still came across. All right, so I'm going to go back and talk briefly about estimating the population standard deviation, and then come back in and finish up this example.